All right, so when we're talking about the way that pulleys behave in rotational motion, the setups for the problems are going to be exactly the same. When we saw these in linear dynamics, the problems would have mentioned something like a massless, frictionless pulley. Or the string rotates without friction, or passes over the pulley. Without friction. Those are keywords for when you can neglect the pulley. Because if the pulley is frictionless, or the string passes over the pulley without friction, then it's actually impossible for this pulley to rotate. So we're going to see that it's friction that actually is going to allow the pulley to rotate. So if they give you any of those keywords, then basically we can completely neglect the pulley. Additionally, if the pulley is massless, then it's going to have no rotational inertia. So even if it was rotating, it wouldn't have any resistance rotation, so you could basically neglect it. So the two ways you approach these problems in terms of thinking about what's going on is either the string is just sliding over the pulley and the pulley is not moving at all and there's no friction. So all the pulley is doing is changing the direction of the string. That's really all the pulley would be doing. Or the system could be spinning, but since the pulley would have no rotational inertia, then it wouldn't contribute to the motion in terms of like inertia or anything. So when we're looking at rotation, I want to examine the rotational aspects of a pulley. They are going to tell you words along the lines that you're going to assume that the pulley rotates or the rotates without slipping, or the string moves with the pulley, without slipping. And so it's kind of this without slipping thing that's going to be the key. So whenever you see this, or additionally if they give you the pulley has to have mass, and there is friction present, you're going to have to include the motion of the pulley. So what does it mean to rotate without slipping? That's going to be kind of the key. Well, from a perspective, if we take a look at like this basic Atwood machine right here, what we do is we assume, first of all, that the pulley first comes in contact with the string. Let's say M2 is bigger than M1, so that this guy's going to go down and this guy's going to move up. We assume that the pulley first comes in contact with the string actually at the midpoint. So I didn't drop it very well here. And loses contact over here at the midpoint on the other side. So basically the string comes in contact with the pulley at a 90-degree angle with the string. And it leaves the pulley when it's at a 90-degree angle with the string, right over there. So that means that our tension forces here, because there will be tension forces pulling down on the pulley, that this tension force here is going to equal this tension force over here. Well, it's not going to equal, but they're both, sorry, they're not equal, but they're going to be 90, the angles are equal. They're both going to be 90-degree angles. So what's nice is when we work the pulleys, we don't have to worry about angles. They're going to be at 90 degrees, so that'll help us out. They could do situations where they're not, no, because even then, it would still leave it 90 degrees. No, it'll be at 90 degrees the whole time. So then what we assume is we assume that this point on the string comes in contact with a corresponding point on the pulley itself. And to rotate without slipping means that those 2 points have the same speed, or the same acceleration. So that throughout the entire motion here, as the string moves, it brings the pulley with it. So that those 2 points move together. If there was no friction, then the pulley would essentially stay in place and the string would pass over it. So as it's rotating, these points stay in contact. And they stay in contact up until this point right here on the outside, where the string loses contact at that point. So those move together. So what that means is that if I look, the tangential velocity of a point on the rim of the pulley has the same linear speed as the string. So we assume that the linear speed of the string is equal to the tangential speed of the point on the rim of the pulley. On the rim of the pulley. So that is what it means to rotate without slipping. In order for this to happen, there has to be friction present. In order for the string to bring the pulley with it, there has to be friction between them because they have to be moving together. But what we assume is that there is friction present, but because they are not sliding against each other, it is a static friction. Because those 2 points are always together, they're not sliding relative to each other, so there's no loss of energy to friction. So there's no loss of energy to heat due to friction. So that means we'll look at this from an energy perspective too next unit, that when you do these problems, that mechanical energy is still conserved. So that's going to be important. So basically, the tangential speed of a point on the rim of the pulley and the linear speed of the string are going to be the same. Now the pulley, because it's rotating about its center axis here, that pulley is going to have an angular speed, omega. By definition, Vt of the rim of the pulley is related to omega by r. So essentially the linear speed of the string is equal to the tangential speed of the rim of the pulley, which is equal to r times omega, which is the angular speed of the pulley. So this is going to give us a way to link linear motion with the blocks, because this is also the speed of the blocks. That's something we assumed with our Atlas machine from the beginning, is that the speed of the blocks is the same as the v of the string. So that the speed of the system is essentially the same linearly, and then we can relate that now to the speed of the pulley in rotation. So that's what's going to kind of make pulley dynamics more complicated, is because we do have both linear and rotation. But it's this idea that is going to be able to bring those together. Now, there is going to also be acceleration. So when we look from an acceleration standpoint, we need to look at more about the forces that are going on. So we know that there's going to be a tension here and a tension over here, because they're pulling, the blocks are pulling down, and those strings are also pulling down, essentially causing a force on the pulley. Now the pulley is going to have a normal force with its axle. It's also going to have a gravitational force. So there's going to be a gravitational force of the earth on the pulley. There is going to be a normal force of the axle on the pulley. So if I was to look at the forces on the pulley, what we'd have to assume is if this thing is not moving up or down. Now I could have a pulley system that's moving up or down. You see those in construction sites all the time. But this, if we assume that this pulley block here is stationary, the axle is stationary, then the normal force here would have to balance the tension, the gravity, and the tension in the other string. So that's what is keeping it in place. So that normal force is going to have to change. And you can imagine that if I put too much weight on this string, that it's possible that I could cause the axle to break or something like that. And then if my normal force can't get high enough, something would have to give. We're not going to have to worry about that. And very rarely will they ask you for that normal force of the axle and the pulley, but they can. In that case, you'd have to add up all the downward forces. Now on the blocks themselves, you are going to have gravitational forces. So we're going to have, say, FG1 here and FG2. And I'm going to assume that FG2 is larger than FG1. So I'm not only am I using subscripts to differentiate between the two blocks, and also here I'm not ever going to use the same symbol if they have different values. But then I also have these tension forces. I'm going to make this guy a little smaller. It'll help with my diagram. So I'm going to have this FG1 here. So I did give these two different variables for tension. When we did Atwood machines and pulleys last time, we assumed that the tension was the same everywhere in the string. But in this case it can't, because we're going to have acceleration. So there is going to be a linear acceleration downward for, not alpha, a linear acceleration downward for this block. And this block is going to have a linear acceleration upward. So in order for this one to accelerate downwards, its tension has to be smaller than the gravitational force. So that we already knew. Over here, this tension had to be larger. And last semester, we assumed that the tension in the string here would equal the tension in the string here. That's not possible this time. Because think about it, why is it impossible for these tensions to be equal? Well, if the pulley itself is rotating and the string, so A of the blocks, so A is going to be the same for each of the blocks in magnitude, and that's going to equal the string, so we assume that the whole thing moves together as a system, then that means there's going to be a tangential acceleration for the rim of the pulley, because they're going to move together, which means there must be an angular acceleration for the pulley. And we know that AT is equal to R times alpha for the pulley. Well, we learned from Newton's second law of rotation that our net torque is equal to I times alpha. Well, what's exerting torque on the pulley? Well, the normal force and the gravitational force are assumed to act at the axis of rotation. So they aren't going to have a contribution to torque. But the tension forces do. So if I'm going to have an angular acceleration, that means that the torque due to tension 2 must be larger than the torque due to FT1 in order for there to be an acceleration, in order for there to be an angular acceleration, in this case in the clockwise direction. FT2 must be bigger. So that means that FT2, because they act at the same radius, must be larger than FT1. So I'm going to make FT1 here a little smaller because they cannot be the same. So FT1 is going to be a little smaller, so I'm going to make FT1 a little smaller here. But what we do still assume is we do still assume that the tension in a section of the string is the same. So we assume that everywhere along this string has the same tension, and everywhere along this string has the same tension. But the string over here is different than the tension over here is different than the tension over on this side. And that is actually due to the presence of friction, because the friction would be acting in the opposite direction of the motion. So if you were to look kind of at what's going along on that rim, is the tension here plus the friction force would have to equal the tension over on this side. And because that's where the difference in forces essentially is coming from. Now you're not going to have to worry about that. You're never going to have to do those types of calculations. Not even in Physics C, just because it's complicated. Because the angles are all changing, lots of fun stuff. So these are the assumptions that you have to work the problem. So now that you have those assumptions, how do you actually solve a problem like this? Well, what you're going to have to do is you're going to have to apply both linear and rotational dynamics. So you're going to have to do like a net torque equation, and then you're still going to need to do your net force equation for block 1, not 0, MA, M1A, and you need your net force equation for block 2. And you're going to end up with a lot of unknowns. But once you've done your rotational equation for the pulley, you've done your linear equation for each of the masses, you're also going to need to use these types of equations in order to relate linear and angular acceleration. So when we actually get to solve one of these problems, we're going to take a look at that. We're actually going to start with this simpler situation with only one block with the string wrapped around the pulley, rather than kind of the Atwood machine, because this is a little bit more complicated. I'll address actually how to solve that problem in a different video.